Okay, so our AVL tree worldview was flipped over a little bit last time when we considered, you know what, maybe we don't have to always balance a tree, or maybe sometimes a tree um, isn't balanceable. So let's flip the worldview over again and think about the nature of searching an AVL tree. Okay, and in parentheses here, we can do you can say BST because an AVL tree is a self-balancing binary search tree, so searching should be the same for those guys. And for the sake of argument here, let me steal this tree. All right. All right, so we have this tree here. Now, when we're searching for data, especially when we consider a binary tree, where when we're putting stuff into the tree, it bounces either left or right depending on where it should go, right? So that means we need to be able to compare one entry to another on some level. All right, so in this case, we happen to be storing what appears to be characters, so chars. We've also stored numbers. If we're searching for the character A in this list, is there a in this tree, is there a differentiation between these three chars, or is every single one of them equally acceptable for finding the value A? What do you think? So I mean, we're searching for data. So the idea is we might be keeping dental records, okay, for a dental office. So each of these guys might be a patient record. And but when we decide if one patient record is less than or equal to or greater than another patient record, how do we make that determination? What would you, if you had some patient records you were supposed to put in order, how would you determine if one patient record should come before or after another patient record? Yeah, maybe you do it by last name. You pick some data point within that object to make a decision, right? Okay, so from that point forward, you're going to be making when you're searching for a specific last name. You might be similarly searching for more information beyond last name, but you've only ordered your data based on last name. Make sense? So the first time you find that last name, you're going to, well, as soon as you find that last name, you're going to be in a situation where you have possibly a false positive. If you have a family, you know, a bunch of Lippmans at the dental office, and they happen to pull up my record rather than my wife's record or something like that, just because of the order in which we were put into the system. Okay, so you know, we're looking at an abstraction of that here where these might be a bunch of last names. Okay, in this case, they're a bunch of characters. So from a searching perspective, and now we're kind of looping back. Remember when we did the different tree traversal stuff and talked about one of the various ways we could walk a tree? All right, and we had trouble kind of putting into context because we didn't have a real example of why you would want to walk a tree in a certain order. So kind of the foreshadowing was, well, sometimes we want to search trees. Okay, well, now we're in a situation where we're also now preparing our trees to be searchable in an efficient way, something like that. So if I'm searching for an A in this tree, isn't this A just as good as this A, just as good as this A? They're indistinguishable in terms of the data that I'm storing here. Okay, they're just as good as each other. Similarly, if I'm searching for a D, isn't all of these equal to each other? Doesn't matter which of those I find. Maybe an initial high level, if we want to not go too deep into the details of this, we might say that if we're just asking the question, is a piece of information a part of this tree or not part of this tree, we're just returning a true or false whether it was found. If I ask, is there a D inside of this binary tree, we would return true. We would start traversing our tree. We would decide, oh, well, it would come to the right of here, the right of here, the left of here. Oh, I found one. Make sense? Okay. Having said that, this tree currently is out of balance right, left, correct? And our trivial right-left rebalancing does this. All right, now we've been operating under the assumption that this is a problem. This breaks the rules of a binary tree. Is this tree still searchable? If I search for a D, will I still discover that it is there? I'm going to have some problems following the binary tree rules getting to this guy, right? That's going to present an issue for me. But having said that, I can still discover that a D is there. And similarly, if I add additional nodes to this, they're going to fall into place and they'll be findable as well. So if I just keep adding more D's, they're going to go into this tree that's kind of a broken tree from a binary, the rules of a binary tree perspective. But the question here is does it break searching? What do you think? Remember, the whole reason we're rebalancing a tree is to support searching. Does this break searching? All right, tell me about that.
I would say yes. I mean, if it's out of balance and it's unsearchable, I would say.
Yeah, but now it's I mean.
But it's illegal.
Okay, but the question is does this guy being illegal make it not searchable? Okay, in what way?
So if that last one was in a D.
So here, let's shift back.
If the last one wasn't on there.
If it was not on here.
Correct.
Okay.
That's still out of balance, right, left. So if you move that other D up to where it was the right child of that E, then it would break searching.
Okay, hold on. So this is what we'd be left with, right?
Yeah.
Okay. Can we still find a D?
You can still find one, but it would, like, you couldn't add things beyond that.
Well, is that necessarily true? So let's add something else to the to this guy. So let's see. Maybe add a F. So we drop the F in, it's going to go here, it's going to go here, and it's going to go here. At the top level, we think that these guys are kind of wonky. They're not ordered correctly, but will the F ultimately drop into what's considered to be a right place? So we have not broken our tree from an ability to add stuff perspective. We got a couple of rule violators in the middle of our tree. But if the whole purpose of rebalancing is to optimize for searching, is this a problem? Again, with the possible false positives, we might find this guy when we actually meant this guy.
And you have to write specific methods or whatever to get down to that portion of the tree. Unless you were searching for something, like if you were searching for F, it probably wouldn't break it, but if you were searching for that particular D, you'd have to write something special for it.
Okay, possibly. At this point, we're looking through the lens of traversing a binary tree in a specific way. What are the various ways we can traverse a binary tree? Okay, and what's breadth? What is breadth first searching, or I think we call that level searching, right? When we looked at it.
It searches to each level.
So we check here, we check here, we check here, then we would check here. We'd find, I mean, if we wanted to be particular about the D we were looking for, we'd find it here. In fact, might we even say that a AVL tree being balanced lends itself to breadth first searching or level searching? The whole purpose is to have it not be too deep, that we only need to go down certain levels of things, right? It's kind of the purpose. When we rebalance trees, we kind of take depth first, in order, post order, pre-order, to an extent off the table, because you're going to omit guys. If we allow a tree to be illegal from a binary tree rules perspective, it was legal when things were added, but when we possibly manipulated the tree, they became illegal. Is that a problem? Given the actual problem we're trying to solve here. We're trying to optimize searching, and is this data still searchable? Which is more important, that it is efficiently searchable from a depth perspective, or that it's efficiently searchable from a find information perspective? If we look at a smaller tree, so let's cut all these guys out. Just do that for now. Don't let me leave this page without repasting that. All right, well, I can always copy back from the other thing. So when I get out of line here and go someplace else, we'll be able to fix it. All right, so we have an out of balance tree here. So we're going to go ahead and fix it. So now we're rebalanced, correct? But we have an illegal tree. So before today, we would have said, we're not allowing this. Broken binary tree. Okay? The rules are out the window. We're not going to allow this. But the whole purpose of rebalancing is to support searching. Can we still find an A in this? Well, if we're not picky about the A's we're looking for, we can find an A right off the bat. If we are picky, and as long as we agree to do level order searching, we'll search through this level. We'll say, oh, we found an A. Is this the A I'm looking for? Well, if it's just the char, one char is just as good as another. But if we use the example of like dental records, where these are the Adams siblings, all right? So this just happens to be their last names, and we're looking specifically for little Jimmy. Okay, Jimmy Adams. So now you're going to say, oh, well, that's not him. This is the sister. We found the brother here. So by doing level order searching, you can find the individual things in there. But you can no longer go down a wild goose chase and assume that all the atoms will be to the left. Because now we've allowed broken binary trees. Make some sense? All right. So with that in mind, what do you think? Should we allow broken binary trees at the cost of rebalancing being simpler? Because remember we said at the beginning that rebalancing is expensive. It's expensive anyways. All right. Well, now if we have to come up with all these special cases where we're kind of doing the crazy stuff with the tree to hopefully get it into a balanced state where it seems like there might be a zillion special cases, is this approach acceptable at the cost of saying, well, we're going to search in level order so we don't omit guys? It's a trade-off, right? Is searching in level order that much slower than searching depth in order? In order, pre-order, post-order, which all assume the same thing. When you go back to our depth algorithm, I think we just have it, display level order or something like that. Let's see. Zoom this guy. Yeah, visit level order. Okay, what did we do? We created some stacks. Then we get the left tree, we get the right tree, but we're not really paying any attention to what order those guys were in. Is the guy we can at the high level say, well, everything to the left is less than or equal to everything to the right is greater than, but at the end of the day, we don't necessarily care about that. So as we're walking through here, we're going to go ahead and grab the first child stack. If it's empty, remember we had the kind of the 3 different levels and we kept feeding off of one and pushing it to the guy at the top. And then when we visited them, let's see, where do we visit? So it's not empty. If it's not equal to null, we're going to go ahead and push the left tree of the child stack onto temp stack. Do the same thing with the right tree, so we'll stage temp stack. That's effectively what we're doing here, right? So temp stack effectively is the guys we want to visit. So now what are we doing? We're going through each of the elements in temp stack. Let's see. Oh, that was for visiting. So we're not actually going through them yet. We're just popping them off of temp stack onto our content stack. Finally, we're going to build it down here. So here's our answer. As long as our answer stack is not empty, we'll just keep concatenating onto that. Answer stack dot pop, get payload. Those are our values. So we'll just remove from that guy, building up a string of all the dudes we're going to visit. So we can certainly approach that differently than just displaying a string. We can go through there and search for specific stuff in there if we wanted to. Is this algorithm inefficient? Just innately inefficient? What would be some things you'd look for based on your experience so far with programming that would start raising red flags about something being extra inefficient? What are some things that you immediately categorize as being potentially inefficient? Okay, yeah, resizing arrays definitely. All right, so that's a specific example. Is there kind of a global operation that, while useful sometimes, should pass through the filter of, are we being horrifically inefficient here? Really one guy I'm hunting for here. Elegant solutions, typically short solutions, but very memory inefficient. So recursion. Right? So recursion tends to be very problematic when it comes to efficiency, especially with large data sets. So the second you start saying, well, we can do something recursively, and on the other side you're saying, well, the amount of data we're manipulating here is large. Those two things are oil and water, right? Because we're going to run out of stack space on the system. We've done that before, where we effectively have something that isn't quite a infinite loop, but it's an infinite enough loop for us to run out of stack space. And if you want that to then work in the Java virtual machine, we have to specifically tell the virtual machine, give it some command line arguments that say, increase your default stack space to something larger, because we'll run out of stack space. All right, so recursion, while elegant, while helpful sometimes, is innately inefficient. Are we using recursion here? All right, so level order isn't immediately off the table as a searching, as a means for searching, right? It was really kind of an exercise in using some data structures we've learned this semester, right? All right, so having said that, go back to our picture here. Is it okay to go ahead and say that we're going to search all of our binary search, or all of our AVL trees using level order searching when we need to get detailed data, when we need to dig deeper into each object? You don't think so? Tell me why. Yeah, level searching. Level searching, we will hit this guy, then we'll hit both of these guys. Even though they're out of order, even though that's an illegal tree. Well, we know if we assume these are characters, just chars, it doesn't matter which one we find first. But now we're going to assume these are patient records. All right, so these are 3 patients whose last names all start with A. Okay, and we might actually be hunting for this particular patient. If we do something that's not a level first search, I mean, at the top level here, where it's maybe less obvious. We might immediately find this person whose last name begins with an A and say, "Oh, this is it. This is the person we're searching for. Done." And we just pulled up the wrong patient record. Okay, probably not going to fly, especially right before surgery. Hasn't it happened before? Like people go in for like amputations and they like cut off the wrong leg and stuff like that.
That's why they use marker and they like mark which limb they're supposed to be operating on.
And then they like make you agree to it. Do you have to like initial it?
My brother can tell me. He had to go in for surgery several times.
Okay, because that would be like kind of the worst.
Well, now they have wristbands and everybody's using skin.
Well, yeah, but what keeps you from taking the wristband off?
Why would you do that? You want to get help. And
Well, not everybody does.
well, I guess some people.
You know, those wristbands actually have a code on them, so if you leave the hospital, like alarms go off.
Really?
Yeah, that happened to my neighbor. He had a panic attack. He bailed. Well, I mean, they can't, but they at least want to be aware when you vacate the premises. So we only live like maybe 3 blocks from the hospital in Grafton. He's running up the street in his hospital gown.
Like running?
Yeah, no, he was out of there. So they sent the police to our house because they were like a missing persons type thing. Because this guy left the hospital and it set off a silent alarm.
I guess that's probably good too. You don't know if people are in the right mind. Like,
Yeah, because like when they discharge you, I think they deactivate the. It's kind of like you have permission to leave. Yeah, it was a funny day. He's a good guy though. He's got some issues. He was a hospital escapee, and they treated him like he was an insane person too. The white coats and everything. Oh, it was awesome. And he hadn't started yet, but he was like getting ready to just like mow the lawn. That was going to be his therapy to like bring him down. Still in the gown.
Why would you change?
Huh?
I guess if you change, you have to wash like 2 clothes.
Yeah, like what the heck? We're already good to go. And it wasn't even anything major. I think it was like an endoscopy or something like that. Probably harder to run out on an amputation.
Yeah.
I would assume. Probably definitely run out, but you get one of those electric scooters. Man,
Catch you pretty quickly though if you were riding one of those trying to get away.
yeah, unless you were like, if you were like techie, you had like a handy friend who was like a mechanic and take the governor off that thing or put a bigger motor on it. A heavily modified electric wheelchair.
It's like Mad Max but with motor scooters.
Seriously.
Well, they goes with bars.
It's like sitting outside the cafeteria, Concordia, in your little scooter. It's like I thought these things were just supposed to have battery operated electric motors. Yeah, this thing runs off a 70% blend of kerosene. All right. So in any case, if we decide to do things with a level order search, balancing our tree in the simplest way possible, already assuming that rebalancing a tree is expensive, can put our tree in something that's more efficient to search in level order, yet technically breaks the binary search tree rules. Given the reason that we balance trees is to increase the efficiency of searching, is that wrong? So last time we broke our maybe our worldview as it relates to AVL trees from the perspective like, oh, wait a minute, maybe we don't rebalance a tree sometimes. Maybe we look at a tree and say, you know what, this guy's out of balance, but what am I going to do about it? All the moves I know put this tree in a state that's illegal. If we make that choice and we decide not to hunt for the elusive special case, which I promise you, for every special case you fix, you'll find 2 other special cases that you still have to fix. So we can decide, oh, well, I'm not going to touch the tree. We're just going to leave it alone. It's out of balance, but what am I supposed to do about it? Or, so that impacts searching as well, right? Because now the tree is deeper. So if we are committing to level order searching, we have more levels to check. So think of it's like if you're checking we'll keep it on the hospital. Okay, if you have a 20-story hospital and you have to check 20 floors, and each floor has 5 rooms on it, that's going to take more time than if you only had to check 10 floors that each had 10 rooms on it, something like that, or at least theoretically that would take less time. All right, so if we're going to allow our tree to get arbitrarily deep because rebalancing isn't sometimes possible, and again, we're kind of rolling the dice on the nature of our data. This is only a problem. Our current rebalancing only breaks, in our mind, when we have data that is duplicates of itself, right? Under normal circumstances, when we're storing a blend of accurate data or a blend of storable data, chances of you getting too far out of balance by not rebalancing is relatively low. Just on the, if you're storing zeros and ones, and you want to be able to search zeros and ones, chances are you want to go ahead and let it illegally rebalance. Put it into a state of being illegal. That way your tree goes wide, but doesn't go 4,000 levels deep. All right, so, kind of the nature of the data is going to drive this. Can we make an official call that one is better or worse than the other? Or does, Yeah, certainly depends on the circumstance. So depending on the nature of the data we're searching, how often we're searching, and so back to the nature of the data, how likely is it that we're going to have seemingly duplicates? And at a primitive level, it doesn't matter. A primitive level, we might as well let this thing get illegally out of balance all day long because we're going to identify the top level one. So even though technically our tree is balanced funky, we're not going to find one of those duplicates, we're not going to have to traverse the weird tree. We'll just get to the root of it and say, oh, we found it. Okay? But in the event, the more likely event, that we're storing object type data that has multiple pieces of information stored within it, but we're storing it based on, like you suggested, last name, something like that. Go to the doctor's office, there might be a lot of people whose last names start with L. Okay? Probably don't want them to bring up the wrong person. Make some sense? Okay. So, circumstantially, we can make a decision on what kind of rebalancing we want to do. We can say, we're going to go ahead and allow an illegal tree. That means always rebalance. Right? That's if we're going to do a level order, kind of a more potentially verbose search. Or we can say sometimes we won't rebalance because it's important that we maintain the appropriate rules of our binary search tree because the nature of the data lends itself to that. Make some sense? Okay, so effectively, with that in mind, we've already written our left-right and our right-left case, just not for the special cases. Okay? So this whole wild goose chase comes back and says sometimes we should rebalance, other times go ahead and, well, sometimes we shouldn't rebalance, or other times rebalance, do it the easy way, and kind of take your glasses off and pretend like the tree's still legal. Because the nature now of that tree is it's a search tree, and the fact that it is not an official legal tree from a searching perspective should not damage us too much. But that tree is still, it's not broken from the perspective of we can still add new elements to the tree, and they will drop at least relatively in the correct neighborhoods. Make sense? Like data is going to be clustered together. All right, so we had to separate those two. All right, next thing we're going to look at. Let's see, I don't think we haven't done Shunting Yard in here, have we? Sounds easy though, right? That just sounds terrifying. All right. Love the Shunting Yard algorithm. All right. All right, so this starts bringing some of our different data structures back into play again. Let me zoom in on this. All right, so the purpose of the Shunting Yard algorithm is to convert. Remember way back when we did in 250, we did process expression, where you had to take in a string like 125 plus 7 minus 2, that kind of stuff. And I think I said something like, oh, you could ignore orders of operation, right? What if I hadn't said you could ignore orders of operation? You actually had to take order of operation into consideration. Okay? It was probably that day that would have been your last day as a CS major, right? That's when you dropped the course, okay? Because if you don't have an algorithm to solve that problem, you don't have the tools in your toolbox to solve that problem, let's see. Unless I put a limit on how long that string would be, that probably was an impossible problem to solve. So that's why I just said, just do it left to right. That way you don't have to do this look ahead thing. Well, the Shunting Yard algorithm is our approach, one approach, to switching our an input string, a math string, into a what's called postfix, or I'm sorry, prefix order. Or reverse Polish notation, if you've ever had a calculator that does that. And those are pretty much stack-based. So you might say, if you want to add 1 and 2 together, you would say 1, enter, 2, enter, plus, enter. And it would add the 1 and 2 together, effectively consuming the plus sign, giving you a 3, pushing the 3 back onto the stack. That makes sense? All right, so as humans, we like writing math things like this. A plus B times C minus D, that kind of thing. All right, but those need to be converted into something else in order for this to work. All right, so having said that, let's kind of walk through the Shunting Yard algorithm. So they have something called an input, something called an output, and then we have our operator stack. So the operator stack we use to put operators onto temporarily while we stage numbers, if you will, could be variables, but numbers on the output stack. All right, so we're going to have 3 different things going on here. So our input, this guy might be a string, and we're going to have to split that string on the operators. We have tools for doing that, right? String tokenizer, we can just, string tokenizer actually is probably the right one for that. We've done that before, right? String tokenizer. So we can just say tokenize on all of our operators, plus, minus, times, divide, what any other operators you want to support. What's interesting about this one is it will also support parentheses. Okay, so because that then kind of throws a weird twist into the. All right. So we'll tokenize this thing to give us the individual tokens, effectively separating our values from our operators. All right, so we can think of this guy over here in input as our tokenizer, our collection of tokens, array of tokens or string tokenizer, however you want to look at it. All right, so we're going to start feeding off of this guy. So when we have something that's a non-operator, like A, we put it onto our output stack. All right, so non-operators immediately go onto the output stack. So we see A moved from here, from input to output. Then we get to the plus sign. We see the plus sign drops down to our operator stack. All right, but there's going to be some caveats there with that operator stack that we have to be careful of. All right, then we hit the B. B moves over. It's on our output stack. Then we hit the multiplication. We're going to try to add, so I'm going to start inserting that word. We're going to try to add the multiplication operator onto our operator stack. And things potentially could happen before we're allowed to get it onto our operator stack. We might need to remove things from our operator stack, making legal room for the guy we're about to add. All right, so multiplication is larger and we'll talk about how these things are ranked here in a second. But this guy has a higher ranking, a higher priority than the dude who's already there. So we'll go ahead and add him right on top. Our try was successful. So we were able to go ahead and put the multiplication operator on top. Then the C goes over to output, ABC. Then we hit the minus operator. All right, so minus operator says that, well, here we can see what ends up happening here. The minus operator, as we try to add it to this guy, notices that, hey, we're trying to put a less important operator on top of a more important operator. So before we're allowed to do that, we need to go ahead and get the multiplication operator out of there. So we're going to pop it off of this stack and append it to this list. Okay, so this guy's a stack. This guy's a linked list that we just keep adding to the end. Okay, or you can think of it as a queue. That's acceptable as well. We'll end up processing this guy from the front, but we're adding to the end, getting to the end of the line, leave the front of the line. All right. So we try to add the minus sign. We notice that, oh, wait a minute, the guy we're adding this on top of is not smaller than me. Therefore, I need to clear the stack. Well, I need to remove the top guy from that stack. So the multiplication will leave and go up here to the, they kind of combine it, but, you know, so I'll speak through it. So the multiplication will leave this operator stack. It'll pop from there and get added to the end of our output list. Then we'll try to add the minus again. And we notice, wait a minute, okay, I still can't get added because I'm still not bigger than the guy that I'm trying to push myself on top of. All right, so the plus sign needs to come off as well. So minus and plus are ties. They have the same level of importance, but we're only allowed to add an operator on top of something where, you know, on top of something that has a lesser value, lesser importance, lesser order of operation. So we tried to add the minus onto the times gets out of there. We tried to add the minus on top of the plus gets out of there. Then we're able to add the minus on top of nothing. So that's when it's finally able to drop in there. So notice the state of our output queue is ABC and then the popped version of the last two guys from our operator stack. So multiplication and addition. All right. Then we hit the D, and the D just comes over to the output stack. Now our input stack is done. We were done processing symbols. So now we just pop the operator stack to empty, leaving us this, okay, which is a reverse Polish notation version of our values. Okay, so just like I mentioned a few minutes ago, and we can actually view this kind of like a stack. Have any of you ever used a reverse Polish calculator before? Hewlett-Packard makes them. If nobody with accounting minors or having taken an accounting class or anything in here. Okay. Okay. Well, you have an accounting minor?
Oh, I took accounting in high school. We didn't get the accounting calculator.
Okay, that was reverse Polish.
We call it an accounting calculator.
Yeah, but they did the stack thing I just talked about, right? Yeah. Well, didn't I say a few minutes ago that that's reverse Polish? You just weren't paying attention? Well, you wouldn't directly put 2 and 2 together. You'd put 2 onto the stack. And you... All right. Reverse Polish or postfix notation. So if we wanted to add 2 and 3 together, we would say 2. So we'd push 2 onto the stack. Then we'd push 3 onto the stack. Then we'd push the plus sign on the stack. As soon as it sees a operator, it's going to say, oh, I'm supposed to do something. Operators consume the 2 guys underneath them on the stack. All right? So we're going to say, oh, this is what I'm going to do. And I'm going to burn through the 3, burn through the 2, perform my operation, which should add them together, which is 5, pushing the result back on the stack. All right, then I could add a 2 onto the stack. Then I can add a multiplication onto the stack. Operator, burn it. What am I supposed to do? Grab the next 2 guys. 2 and 5, multiply them together, giving me a 10, push it back onto the stack. Make sense?
So does that only work with single-digit numbers then?
No. The numbers here, if we do our tokenizer and we had 10 times 17, the tokens would be 10, multiplication, 17. So 10 would move over here and the 17 would move over here as individual little pods. And we should be okay because we're storing them as kind of the nodes of the linked list. All right, so in the end, this guy here looked like this was our final thing, ABC times plus D minus. So ABC times plus D minus, and let's just go ahead and replace the those values with some numbers. Okay, so this is the order in which we're going to be pushing things onto our stack. So we would push on a 1, then a 2, then a 3, then a times. Times says, oh, we need to go ahead and consume the 3 and the 2, and actually, just as a starting point, let me show you what this started off as. So this was A plus B times C minus D. A plus B times C minus D. Is that right? A plus B times C minus D. So if this is 1, this is 2, this is 3, this is 4. So the very first thing we should do as human beings, we can immediately recognize that the 2 times 3 is the order of operation that happens first. So that should give us our 6. So as we push as we start walking through this, we push the 1, we push the 2 on top of that, we push the 3 on top of that, then we hit the times. This is an operator. We need to consume the next 2 guys. That's 3 and 2, multiply them together, and that's going to give us a 6. All right, then we hit the plus sign. All right, plus sign says, oh, well, we have an operator. What do we need to do? Consume the next 2 guys, add them together, push the result back in the stack. Is that the next thing that should happen? Plus and minus are equal, so we do left to right for order operation. So the next thing that should happen is 1 plus the result of 2 times 3. 1 plus the result of 2 times 3. So this is going to give us a 7, pushed back onto the stack. Okay. Then we push on a 4. Then we push on a minus. All right. So now, this is where we have to pay close attention to how we grab things. What's the left operator? What's the right operator? We know that this is what happens first. That's going to get us down to a 7, right? 1 plus 6 is going to give us a 7. So the way this next thing should work is it should give us the result of 7 minus 4. So the first thing we pop off, the first number we pop off, will be our right operator, followed by our left operator, or left operand, sorry. Right operand, left operand. So when we say process the minus, this is going to say 7 minus 4, which will give us the 3, pushing the result back on there. At that point in time, this stack is empty. You can think of it as a stack, this list, whatever it is. We're out of stuff to do. Our final answer is sitting right there at the top of our answer stack. Make sense? All right. So that's a simple version of Shunting Yard. Hence the simple conversion. So understand Shunting Yard there's 2 sides to it. Well, 2 sides to what we're ultimately trying to accomplish. The actual Shunting Yard algorithm says, how do I convert from postfix to prefix? That is, how do I convert from a mathematical expression where the operators come after the operands, or sit between them, to they actually come before what they should do. Make sense? So we're reordering those things so that we can do that stack, the stack math we just talked about. All right, so this kind of goes through that. This really just goes through what we just said. All right, so here is an order of precedence, so we can give a value to each of these guys. So minus and plus, we can say they have a precedence of 2, times and divide, precedence of 3, something to a power, precedence of 4, you know, if we're going to support powers. All right. So now, what if we started incorporating things like parentheses? Okay, how do we handle parentheses? I don't want to use that example. Yeah. We'll use this example. All right. So let's start walking through this guy. We'll go in here. So that is our starting point. All right. And so this is a 2, a 2, I'm sorry, a 2, a 3, a 3, a 2, a 4, a 4 in terms of their order of operation weight, their power. Okay, and that comes into play when we go to add something from our input list into the operator stack. We cannot put something on top of something that is less than or equal to, we cannot put something on top of something that is greater than or equal to it. So that means we cannot put a plus sign on top of a minus sign. The minus would pop off. We can put a multiplication sign on top of pluses or minuses. We cannot put a division on top of a multiplication because they're equal. Make sense? The multiplication would have to pop off first. All right, so now our new question is, how do we handle the parentheses? That's what we're looking for with that. All right, so we can start processing through this guy. So we're going to have 3 stacks. This is going to be output. Well, we'll just 3 things here. So output, op, okay, and then this guy is our input. So we'll copy him down there so we can leave that as a full string, but remove from this guy down here. All right, so this is input. Very first thing we process is this first token, which is a 3. 3s go onto the output. So that guy's now been processed. Then we hit the plus sign. Okay, we're going to try to push the plus sign onto our op stack, and it's a successful endeavor. So we process that guy. Then we hit the 4. 4s will go onto the end of our output stack. Then we hit the multiplication. We try to push that onto the op stack, and it is successful. Well, let's see where. Yeah, so the top of my stack is going to be here to the left. This really should be vertical, but so top will be on the left. So I just push the multiplication on top of the plus sign. All right. Then we hit the 2. Add that to the end of output. Now we hit the division. We're going to try to push that on top of the multiplication unsuccessfully. Multiplication needs to pop off, leaving the op stack looking like this. Then we're going to try to push division on top of the plus. Is that allowed? Yep, we can do that. So division's on top of the plus now. Okay. All right, so now we hit something weird. We have our parentheses. So we go back to algorithm here. Let's see, here's our output stack. So notice we're sitting in this situation right here, where our output stack looks like division plus. So it looks like we're legit up to this point. All right, so we have 3, 4, 2 times, then division plus, 3, 4, 2 times, division plus. So we're so far so good. We understand the basic algorithm up to this point. All right, so let's go and see how we handle the parenthesis. So parenthesis, that's going to be the next guy we read in. So that's over here. That's from our, this is the next token. So we grab the next token from our input, okay, and we're going to push that token to our operator stack. All right, this guy can go on top of anything. All right, we're going to say that's okay. So when we try to push an opening parenthesis, it's successful. So we're going to go ahead and get that guy. We'll push him on top of that. All right, and that's successful. So now our op stack looks like this. Then we get the 1. So we can keep chugging along here. 1 gets added to the end of output. Then we get the minus. Okay, well, what happens? Okay, can I put a minus on top of a open parenthesis? Yes, I can. So open parentheses have, they're almost like non-members. Okay? We kind of ignore them. They serve a purpose, and the purpose they're going to serve is they become the stop point when I do I pop a bunch of stuff off the op stack. We'll see that here in a few minutes. So what do we do with the minus? We go ahead and push it on top of the op stack. Then we hit the 5. We love normal operands because they're pretty easy. We don't have to do any logic. Just move them to the end of the output list. Okay, now we've hit a closing parenthesis. So what do we do with closing parentheses? All right, so here's our closing parenthesis. Closing parenthesis says pop our output stack until we get to the opening parenthesis. So we just moved the 5 here. Then we hit the closing parenthesis. We're not going to even try to put the closing parenthesis onto the op stack. At the end of the day, the parentheses are meaningless. They're not going to make their way onto our output. Right? They're placeholders to make sure that we put things into our output queue in the right order. Okay? So when we hit that closing parenthesis, this flags us and says we need to go ahead and pop our output stack, or pop our op stack, until we hit that closing parenthesis, or the opening parenthesis, sorry. So we're going to say, is the peak of our op stack the closing or the opening parenthesis? It's not. So pop it and add it to the end of output. Go back. Is the peak of our op stack the opening parenthesis? It is. I've finished this set of things. All right. So the minus goes where it's going to go, and now I'm going to burn this opening parenthesis. It's no longer necessary for what I've been doing. All right. So discard the matching parenthesis. So I'm going to go ahead and just get rid of that guy. The parentheses have done their job at this point. So this was the token I just dealt with. He never actually was stored anywhere. He was just my marker that said, okay, I need to burn my op stack until I find the matching opening parenthesis. And once I've popped everything from my op stack and put it onto the end of the line, the end of the queue on our output, then I can go ahead and burn that original opening parenthesis, the matching opening parenthesis. Okay, now we're hitting normal operators again. So we hit this guy. We're going to try to push that guy onto our op stack. Are we allowed to push him onto the op stack? Remember, that guy had a value of 4. Doesn't really matter what we say those values are as long as in the right order, right? So this guy is, as far as we've advertised, the guy who weighs the most. Okay, and we're omitting, I mean, there's a whole big list. We can say put sines and cosines and all sorts of stuff on there. We're not going to go that deep. We're just going to stick with these things. This is going to be the extent of the things we're dealing with. So we're going to try to push that guy onto the op stack, and it will be successful. Okay, then we're going to hit the 2, and we can see that it was successful to put him onto the op stack. Then we're going to hit the 2. Goes goes to it's an operand, just goes to the end of the output. Then we hit this guy. We're going to try to push him onto the top of the op stack. Are we successful? We're not. Not successful. You might not be able to tell the difference, but this guy is a different guy than this guy. Okay? They're equal to each other in power. We can only push on top of something that is less than us. All right, so we're going to have to pop this guy off, put him onto the end of output, and now we can successfully put that guy onto the top of our op stack. Looks the same. All right, but it's important that we recognize that we first needed to pop the other power operator before we could push this guy. All right, then we deal with the 3. Now we're out of input, so we pop until op is done. All right, and this should be the output of Shunting Yard. So 342 times 15. 342 times 15 minus. Ooh, hold on a second. Oh, this is the left to right stuff. Okay, I got to introduce something else up here. Notice that the power guy here has what's called right associativity. So this guy says we are allowed to push on top. So because it's operated from right to left instead of left to right, I guess we treat that guy as kind of a special case. So with that in mind, let's just back up here for a second to that point. Right there. When we try to push this guy into the op stack, it succeeds. Not, see, up to this point, we never dealt with this before because we always said, oh, well, this guy has a value of 4, and 4 is not greater than 4. In this case, since this dude has a right associativity, that's a tough word to say, isn't it? That should be next week's quiz. Just say the word.
Pronounce it.
Just pronounce this word. First try though. First try. You gotta.
All weekend wrong here.
Just practicing. It's like a. You can't say that word, can you? Well, did you practice that in your head first, or is this like?
I have to practice all words in my head first.
Oh, so that this was natural to you. Okay, so. You weren't just showing off. This was just the way you. I get it. Yeah, because I'm incapable of saying that word. Associativity. Is that it? Associativity. Nailed it. See? I'll never mess it up again until the next time. Okay, so with that in mind, since this guy is a 4, but it's right associative. All right, that means we are allowed to push it on top of the stack. That guy is a special case. All right, so we are allowed to push that on top of the stack. Then we add the 3 here. Then we burn the stack. So this will be power, divide, plus. Okay, so 342 times 15 minus 23. 342 times 15 minus 23. Power, divide, plus. Power, divide, plus. Make sense? All right, so that associativity thing is kind of a special case, and we'll just introduce that one guy there. I think there's some other ones, like I think sines and cosines might work the same way, but we're not going to go that deep. We'll just have this one special case in our world. But basically what we're saying is we always have to ask the if statement. When we try to push an operator onto our op stack, we need to say, first of all, is the guy we're pushing right or left associative? And how does that impact the guy that's already on the top of the stack? You know, if they're both right associative, actually, let's think about that. In our world, it wouldn't make a difference because all of our left associative ones are going to be less than the right associative ones. So it's going to it'll require us to pop anyways. So it won't have it won't be a problem. If I try to put a plus sign on top of a power, it's not going to go. We're gonna have to pop the power. The associativity thing, pop the power. That's like a Power Rangers thing, isn't it? I think so. Yeah, it must be.
Sounds like you're taking drugs,
Pop the power. Actually, isn't that wasn't there a whole thing on that? Was it the superhero guy who's like all about the elements? Like he's Captain Planet. Yeah, wasn't there something that he says that people were saying that he was basically popping pills or something? I don't remember.
I haven't watched Captain Planet.
Yeah, see, I think I read it in one of the sidebarred ads when I was reading My Little Pony fan fiction. But no giggle. You giggled a little bit. None of you read that. You're in the adult coloring books. You know what My Little Pony is, right?
I've watched a documentary on it. It's really interesting.
But you don't read the fan fiction.
No, I don't.
Oh, it's a shame. I use it in some of my other classes when we need to have like a placeholder text. Just like a paragraph or something. One time I just randomly thought of that and I just went and searched for it and it's real. There actually is My Little Pony fan fiction. So we just copied a big, what's this?
Bronies are weird dudes.
Yeah.
They're really weird.
Bronies.
Yeah.
Is this a new word? I just learned a new word.
Yeah,
What's?
that's what like the adult male following of My Little Pony is called.
Oh, why do you know that?
No, I
I
knew
go
that
on the
too.
internet a lot.
I feel like that was common knowledge.
Yeah, that was the documentary that I watched on
Reddit.
brownies.
They're usually not very good people, so you kind of want to steer clear.
Okay, so bronies are adult male followers of My Little Pony. What does it mean to be a follower of My Little Pony?
You watch it.
A cult. It's a cult.
Man, they have names? Like, wow.
They came up with the name.
They're called-
Not all the
They're
time.
called bronies, like brothers and the pony, right? Yes, and I'm a little concerned. Are those the ones that were writing this fan fiction I'm using?
Most likely.
So like my IP address is like getting included. I'm going to be on a mailing list. I'm going to start getting Amazon gift cards from the bronies. I'll take a free Amazon gift card. Wow, yeah. Isn't that? I think there was an episode of John Oliver or something like that where he said, "Come up with anything as crazy sounding as it might be. Look for it on the internet, and it probably exists." Isn't that messed up?
There was someone at work the other day that they found it was like a paper and dice game, and it was called Pocket Dungeons. They were trying to find videos of Pocket Dungeons. They looked it up, and apparently there's also like a BDSM kit.
Yeah.
It's also called Pocket Dungeons. Like you're getting like unboxing.
The unboxing videos.
I guess.
It's like equivalent to like when somebody gets like a new iPhone or an Android device and they have like the the Galaxy S7 unboxing. It was that, but for that.
I guess.
Wow.
If you can think of it, it's probably somewhere on the internet.
Well, I could just check with you. Well, actually, I think I am a little concerned that you knew it as common knowledge about these bronies. Well, no, you knew
There
it.
was a brony con.
Yeah, there's a brony con. There's cons for everything now.
I just looked it up. There's like this hate website hating on them, telling them that shows for little girls.
All they passion.
Well, I didn't even know there was a show.
They had a recent reboot.
Because when I was a kid, they were toys. I don't think there was a
There's
show.
like multiple
there's-
generations of the show too.
The most recent one is the one that brought up the bronies. I forgot what her name is, but she did the Powerpuff Girls. She did a reboot of it.
Okay.
And a lot of people really got into it.
Wow. We live in a kind of messed up world, don't we? You got the adult coloring books. You got the bronies.
4chan.
The who?
4chan.
4chan? What's that?
It's like Reddit, but terrible.
But not good. But so it's like a Reddit competitor.
Yeah, kind of.
Well, that's less weird than bronies.
There are some parts on 4chan that are really out there, like date, random. Don't go on random. It's also blocked by the
If the campus blocks it, don't go there.
Yeah.
I recently had an issue in my 450 class where the campus is blocking. We were trying to do socket programming to an SMTP server, and the campus blocks it, so we had to use a third-party host to talk to it. That was not whatever this was. It was completely legit. All right, so questions about the Shunting Yard algorithm. This make sense? So we think we understand it enough to write this? Really? Just the first part, not the processing of it. So what we're going to do, well, make sure you're very careful when you're typing this. It was an incident once. So, and the funny thing is, it was the spelling corrected to the incident. All right, so we're going to create an Android app. You can just do this as another screen on your app that has a single text box, which takes in a postfix formatted string, i.e. something like 125 plus 7 divided by 2 plus 3 times 4, something like that. We'll just kick this down on this line. All right, so that might be sample input, and it should convert that use the Shunting Yard. That was the double the double typo. That would have been a problem. Your program should use the Shunting Yard algorithm to convert this. Convert into postfix order. It should support plus, minus, times, divide, power, open, close parentheses. Those are your operators it should support. All right, so for your homework assignment, the input's going to look something like that. The output should be the equivalent postfix for this guy. So if you want to think of it like one of these examples here, if the input looked like this, output for this example would be that guy. So that's what your program should produce initially. Make sense? Questions, comments, concerns, bribes? All right. I will see everybody on Tuesday.